Okay, hello. We are here to talk about why we should put secrets in Git. Because you've all learned this, right? That you should put secrets in Git. And yeah, you came here to know what the F is he talking about. But of course, it's just bait because the real name of the talk is why we should put encrypted secrets in Git. So yeah, I kind of ruined that already. So why Git? Your Git repository, it tells a story, right? It tells how your code base has evolved. It tells about your data schema through migrations often. It's version controlled. Your configuration, your app settings, your package.json scripts. You get Git blame, right? You can see which colleague introduced the bug to production. You have a distributed backup of all the code on everyone's machine. That's great. We can do atomic changes that prevent drift, because we usually have our infrastructure as well, right? As infrastructure as code together with the application which runs on it. Disaster recovery becomes easier, and if we're doing GitOps, it even is the source of truth for the state of how things should be. But hopefully your repo doesn't tell this story. Secrets, we just can't get rid of them. We need secret in the applications we make. There's a lot of ways of getting around it these days with policies and managed identities and that kind of stuff, but it's still a part of what we do. You probably have your .ven file, maybe git ignored, maybe that secret is not for the production environment, it's just for the test environment. But as developers, we often follow the path of least resistance, right? So who here has sent a .env file to another developer on the team to onboard them? Exactly. I did that at the Booster conference, and like almost nobody raised their hands. I was like, you are a bunch of liars. Everyone has done that, and it's only natural, but usually we weigh the risks. But the point I'm getting to here is that by including secrets in Git, we kind of complete the narrative. It's kind of the last missing piece of the puzzle to version our secrets together with the application and infrastructure that uses them. So yeah, that sounds good. Like, yeah, let's put encrypted secrets in Git then. But that's the easy part. But how do we take those secrets and make them available for the application? And kind of how does encryption work? Okay, we put it there encrypted, but if our application is going to use it, it needs to be able to decrypt it. So to get into that, I just wanted to quickly kind of get into how encryption works. To do encryption, we use keys and algorithms, right? But basically, we need keys, and as it says here, we can encrypt and decrypt, or we can one-way encrypt, kind of hash, and you could never retrieve it. But in our case, we're interested in kind of this two-way part. There exists two types of keys. One is symmetric keys, and it's basically you all have the same key, and it can both lock and unlock. The good thing about symmetric keys and why this is what we actually use, it has to do with it's really fast and effective. So mathematically, it's the best thing to use when we're sending a lot of data through the internet, right? And we want it to be encrypted, and we have to decrypt and encrypt all the time on each side. But key management is complicated with symmetric keys, and of course, if one party loses the key, both sides are kind of compromised. And yeah, if you used one symmetric key to talk to 100 different people, you would need to handle 100 keys to not lose control. You would lose control, is my point. So we have asymmetric keys, which is a key pair. And this every developer uses daily with kind of SSH key for pushing to GitHub, or you have a SSH key to log on a server. But also every person in the world uses this every day, because this is how the internet works, through HTTPS. So you have two parts of a key. You have the private key that you never share to anyone. You keep it safe. That one can be used to decrypt things that have been encrypted with the public key. And it can use to be signed signatures, which can be verified by the public key. So you can give the public key to whoever you want. They can encrypt a message to you that they know that only you can decrypt. Or they can see a piece of information that you have signed with the private key and know that there's no deniability that key actually signed that message. But still, when we use asymmetric keys, the goal is to achieve a symmetric key because of speed. So in communication, we use asymmetric keys or certificates, or which is basically asymmetric keys, and we get a symmetric key because that's fast and one key for everything. But the problem with handling keys like this, I'm sure you all have a .ssh folder on your machine with some keys in it, and yeah, maybe you get a new Mac and then that key is gone. Ah, shit. Then you add a new key on your GitHub and you keep going, right? So it just shows that kind of managing keys is hard, and this kind of initial trust. If I got a public key from someone, how do I know that person is the one that gave me the key, right? If it happens over the internet, that initial trust, we call it, is very difficult. So, luckily, I'm going to introduce you to a tool right now that kind of helps with all of this. It's called SOPS. It stands for Secret Operations. It was initially launched by Mozilla, but has been given to the CNCF sandbox. So it's kind of open source, is basically what I'm saying, with complicated organizational names. It was inspired, of course, by many years of managing PGP encrypted files and keys. What makes SOPS a bit unique compared to tools like Gitcrypt that can do like binary encryption of files is that it actually can partially encrypt files. So as it says here, YAML, JSON, NVENIM, and also it can do binary. But it means you can keep a lot of the information and metadata of the file. And another great thing about it is that it has support for secure storage in most of the big cloud providers, but also standard PGP keys. So I'll get back to that and show a bit about that. But it's basically just a CLI tool that you run to encrypt and to decrypt. So the selling point of SOPS is that it removes the impracticalities around key management and initial trust. And I'll show some examples. And of course, the world runs on YAML these days. I'm going to show you YAML. But you go to a dev conference these days, that's all you get anyway. This is .sops.yaml. It's kind of the configuration file, lives in the root of your repository. In this example, we're basically saying, we're not saying encrypt all YAML files. We're saying if I encrypt a YAML file anywhere in a subdirectory of this folder structure, look for fields called where the key is data or string data. And if you ever worked with Kubernetes, this is targeting a resource definition of a Kubernetes secret. And it has here pointing at the PGP key that is on my machine. And in this example, I have both the public and the private key, so I can both encrypt and decrypt. In reality, if I wanted to just encrypt and commit to the repo, I would only need the public key. But in the example here, we want to be able to decrypt as well. So if we look at this secret.yaml file, this is just a normal resource definition of a Kubernetes secret. And you can see it has some string data. And this is a nice little home lab example, right, with Photo Prism. And it runs on MariaDB. So it has basically 3 passwords. And if we use SOPS on this file, based on the sops.yaml that we had before, as you can see in the gray under here, we just run this command and we pipe the result out to a new file called secret.enc.encrypted.yaml. That file will be encrypted, so that one we can check in to our source control and version control. But the cool thing is that if we look at that file, we'll see that it actually looks a bit the same. If you start reading from the top, you see we're preserving all the Kubernetes resource definition metadata. But if we have a look at the string data, we'll see we kept the keys, but the values are gone. But they're not either. Also, the value is not just binary data. It's actually metadata inside there about what was used to encrypt it and things to kind of find out for SOPS to know how to decrypt it. But this even though I use my PGP key, this is not encrypted with my PGP key. This is, SOPS has created a symmetric key to encrypt these values. And then it has, in all this metadata below, it has encrypted that symmetric key with my public key from my asymmetric key. The reason we're doing this is, again, key management, because you maybe want several people, your whole team, and maybe some backup keys to have access to this one. So this is a way of making sure that we can share that symmetric key with a whole team, so more people are able to decrypt the file, and we can add more people later without having to encrypt again the actual secrets. We can just re-encrypt the symmetric key used to it. So it's kind of a key locked away with a lock that can be opened by another key. So it gets a bit complicated, but this is all handled by SOPS, so you don't really have to think about it. But again, it's just symmetric and asymmetric keys, the same way as the rest of the internet kind of works. So, but of course, if I now deploy this with GitOps to my Kubernetes cluster will have to be able to decrypt it. So does that mean that my Kubernetes cluster needs its own key? Yes, it does. That is correct. So here's an example where I actually take that key that I said I had on my machine, I export the secret key, the private key, and I create a Kubernetes secret. Here, this is with FluxCD. You could use Argo or whatever you use. It supports that, or you can just do it manually with the command line. And I can put that in Kubernetes, and since FluxCD has support for SOPS through its secret handling, it can just understand when it gets a resource, it can see that it has the SOPS metadata and understands, yeah, I have to decrypt it before I put it in the cluster. So here's just showing the secret living in the cluster. So it's encrypted in your Git repository, and when the GitOps, when FluxCD or Argo or whatever pulls your Git repo and updates, then it decrypts it on the machine inside the cluster and creates the secret. So you have this encryption in transit as well, double up. After I've done this, I could also delete the private key from my machine and just only have it living in the cluster, for example. And I could just take the public key. The public key is, you can't do anything dangerous with the public key, so I could actually check it into the Git repository and say every time you need to update a secret or add a new secret, use this public key that is in the Git repository to encrypt it and just deploy it, because the cluster will know how to fetch it, but you are not able to do it. But that can be a bit impractical, and yeah, maybe smart to store that key somewhere, probably offline. Everyone working with encryption and keys, they just want you to print it out and put it in a fireproof safe and put it in your mom's basement or something. Offline storage. So yeah, here's another example. And now we're getting into a bit more interesting part. Here you can see it's a lot more. You can see I'm keeping my PGP key, but I'm also adding Azure Key Vault as a key from Azure Key Vault. The reason I'm keeping my PGP key is because you should never put all your eggs in the Microsoft basket. So I'm just using that to have a backup in case, I don't know, Microsoft deletes my Azure Key Vault where the other key is. So that's just a safety measure. But here you can see, this is just a nice example of seeing that the first rule just says that if I'm encrypting anything inside the secrets prod folder, it should use a different key from a different key vault, which has different access, right? And the whole point here is that we're actually creating a key in a key vault, so we don't have to handle a key at all, right? We want to get away from this key management problem, and we just want to log in. So the cool thing about this also is that I can basically get infrastructure as code for my key that I'm using as well, right? So in this example, this is a very lightweight example of creating a key vault, and we basically give a group access. Our developer group, our team, can get access. Here I'm giving key vault administrator. It's not really maybe the best to give to everyone, but for simplicity's sake, we're doing that here. And we are creating a key, which we're just calling the shared SOPS key. And we're saying people who have access to this key should be able to encrypt and decrypt, right? And this has now been kind of access controlled by the same way and the same groups that we use for our other infrastructure in Azure. The cool thing about using Azure Key Vault for the key is that they actually use like secure HSMs, like secure hardware storage, specialized hardware to store the keys. And you also get complete audit logging, who has accessed the key and used what operations with the key. And you can do simple things like this as well. You can say that this key, it shouldn't be able to export it. So Key Vault kind of becomes your little YubiKey, because that's the special thing with the YubiKey. It's also asymmetric keys, but the private key is not possible for it to leave the little YubiKey. So you actually send thing and you encrypt it, and that way the key is much more secure. So the cool thing is now we can do a second round, and I can actually start like, yeah, for all my infrastructure as code, I can actually I can have my secrets that I want to have in a Key Vault that our application use. I can have that in my Git repository, and I can encrypt it. So if I run SOPS on this one, it will just make it into a JSON file with data and all that SOPS information on how to decode it. So I can do like binary encryption of any file, basically. But the metadata is kept as much as it is. But for this, since it's not a JSON or YAML, it doesn't do that partial encryption. So back to the .env example. If you now had this .env file with a secret that all developers need to actually test the application locally and do development, because this is the login, then I can actually just run SOPS and encrypt on it. And now it will look like this after. You'll have all the metadata in the .env file. And you'll see that the client secret, the top one, is encrypted. But the good thing now is that the only thing I need to do as a new developer pulling the code and the code base now is to just log in and run SOPS decrypt. So I log into the Azure CLI, and I'm in the developer group. I was added to that when I joined the team. I take down the repo, I log into Azure, and then I run SOPS decrypt. It will see in the .sops.yaml file that, it's a key vault that was used for this, and we'll see in the secret metadata, it's this key. And it will just go fetch that key. Now I have access to it because it uses the Azure CLI to do that under the hood, pulls the key, decrypts the file, and I have access to it. So the developer experience is just signing in. Of course, there are some gotchas. SOPS security, it kind of depends entirely on key management, but here we're giving the key management to a Key Vault, right? We're making sure we use the same login and MFA as if we are logging in to check something in Azure in the portal, right? So, but yeah, there are routines on how to cycle secrets and everything, but yeah, probably the last one is kind of the most important one, right? But I think the pros outweigh the cons in this. Anyone know what this is? Quantum computer. So yeah, everything I told you now about asymmetric keys and symmetric keys, this bad boy, it will destroy it, and the internet and everything is, we're gone. This is from the Gartner 2025 Top Strategic Technology Trends report. And yeah, current encryption will break is the expectation of quantum machines. So already now we are under attack by quantum computing in a way that in what we call a harvest now, decrypt later attack. So people now are trying to store data. So when quantum computing potentially breaks the encryption we have today, they will have all the encrypted data ready to go to decrypt it. And you also have Shor's algorithm, which basically if you have the public key, you can calculate the private key. That's impossible now. But with quantum computing, we expect it to be possible that if you share your public key with me, I can calculate the private key. And of course, then the whole internet as we know it would break if that was possible. So there's some good things to read about quantum computer, but it's let's just wait till someone tells us what to do, I guess, in this one. Thank you.